Afternoon. My name is Wenming Yi. I'm a technical evangelist on the Windows Server Evangelism team. So today our session is about taking high-performance computing to the cloud. We're going to talk about the Windows HPC and Windows Azure. So the door is just closed, and we'll get started in about a minute or two. All right, according to my clock, it's exactly 1:30, so I'll go ahead and get started. So once again, my name is Wenming Yi. I'm a technical evangelist on the Windows Server Evangelism team. And I mostly have been working on Windows HPC for the last 3 years, working with the product team and helping them to understand our customers, as well as helping our customers to understand the actual Windows HPC product. So I am the middleman for helping the product team, as well as our customers. So here's today's agenda, and I put down three goals. The first one is to try to help you understand what the difference between on-premise HPC and Windows Azure by itself. And the second one is to take a look at the new product that we have made, which is Windows HPC R2, SP2, which has a built-in hybrid cloud engine right there inside the product. And third is I want to take a look to see how you actually programmatically scale up inside the cloud and also scale out to multiple nodes. So those are the three goals. And here's how we're going to get there. And the first thing is that we'll do an introduction. For those of you who are not familiar with HPC, I'll do a very quick and brief introduction of that. And then we'll look at three different types of hardware configurations. One is to have your HPC application running entirely on Azure. And the second is to look at how the on-premise or the traditional HPC works and how their applications are different from regular computational intensive applications. And third, we'll look at the integration of Windows Azure inside the HPC Server 2008 R2. So this question has been asked many, many times during the last 3 years that I have been with Microsoft. What exactly is HPC? So I've actually changed this slide at least 10 times by now. And I've come to the conclusion that the next 3 to 5 points is actually the best summary for what HPC is. First, we are not really worried about what the hardware is. We're worried about what the actual problems we're trying to solve. So the type of computational intensive problems are usually associated with time, space, complexity. So in time, it means CPU. So you're using as much CPU you can throw at this particular problem. And space, here we mean disk space or memory. So a lot of these applications require significant amount of memory to run. So sometimes in the terabyte range. That's why you need a clustered environment. So that brings us back to massive parallelism. So in order to run a problem that requires terabytes of RAM and many, many years of computational time in terms of a single PC, you're going to need parallelism. So the way we're going to be able to do that is through cluster-based systems. So the difference between HPC and a regular computational intensive job is that it requires high bandwidth and low latency, and they're usually cluster-based. So for high bandwidth and low latency, I am talking about specialized hardware. For many of you probably have seen the InfiniBand now is capable of doing 100 gigabps. That is 100 times the speed of a normal Ethernet. And also, you're not just worried about the high bandwidth. You're also concerned about the latency, the latency of communication between the nodes. So the latency, we're now talking about 1 or 2 microseconds in terms of the actual latency. And comparing that to Ethernet, we're looking at 70 microsecond or more. So this is why HPC is extremely expensive in terms of cluster software, cluster hardware that you're buying, and it's essentially the car race or Ferrari of your car industry. In the computing industry, HPC is what every vendor would like to show off, where every vendor like to show off their latest and greatest hardware. And now, since the hardware is becoming cheaper, as you can see from the timeline below, in 1991, you're looking at getting 10 gigaflops worth of machines for about $40 million. Who has actually used this Cray YMP before? Anybody has seen this machine before? So that machine wasn't made too long ago, and in fact, I actually used it at NCAR. NCAR is the National Weather Research Center in Boulder, Colorado. And this is 1991 is really not that long ago. And then for $1 million, 7 years later, you can have the same computational power. And in 2008, when I started writing these slide decks, it gotten to be about $1,000. And now I think your laptop is fully capable of doing just as much computational power as a $40 million machine almost 30 years ago. Or is it 20? 20 years ago. Okay. And for these machines, you traditionally always need a specialized staff. And just happened to be that I have a Cray CX1, which is a blade, 8-node, with a total of 64 core and 128 gigabyte memory machine. Even though it is for desk-side computing, you're still looking at sometimes requiring specialized services. So now let's take a look at the goals for the HPC product, or for anyone who's trying to do HPC. So I came up with this just to make sure you can take something away and remember. So this is the 0-1 infinity rule or goal for computational intensive jobs. One is that your initial investment or barrier for entry should be as small as possible. So in terms of clusters, hardware is getting cheaper and cheaper. You can get gigaflops of computational power for very little money. And in terms of efficiency, you want your application to fully take advantage of your clustered computing hardware. So if you have 1,000 nodes, each with 8 cores, that 8,000 cores better be utilized fully for you to justify buying these type of hardware and also buying the clustered, expensive InfiniBand and those hardware. And also be able to scale your application to as many cores as possible. In traditional HPC, there's a lot of life science codes that scale up really, really well. And for DNA sequencing, quantum chemistry, those type of codes can scale out all the way up to 120,000 cores. So last year, you probably heard that the Jacquard is, I think it's Jaguar was still on the top 500 list as number 2. Now there is a new computer which they built in China now as the the number 1 in top 500. So what they did, instead of having just CPUs, they added GPUs on top of these machines. So suddenly, you have a tremendous amount of computational power. Of course, there's no such a thing as free lunch and parallelism. GPU, you would have to rewrite your code to work with GPUs. And we're going to take a look at how we are going to take your traditional HPC applications and look at the differences between Windows Azure hardware versus Windows HPC hardware and see what kind of application you can actually run versus the type of thing that you cannot run yet on Windows Azure. So the question here is, how do you take existing technical computing applications and move it onto Azure? And what are the things that you can do? And we're going to focus on that. Focus on things that we can do versus things that, instead of things that we cannot yet do. So we're going to talk about these different scenarios. And here is a diagram of my Cray on the top right corner. as you can see. So this little box has 128 gigabytes of memory. And I think it costs somewhere about $100,000 if you buy it retail. Of course, we got it a bit cheaper. And yes, you still have to maintain it for staff power, backup, internet storage. And I think over the years, it has used a lot of electricity while it's sitting in my data center. So I think it has, when it's idle, completely idle, it's using about 600 watts worth of power. So when I have it fully running, if I have all the CPUs running, you're probably looking at 3 to 5 times the amount of power that it's than when it's sitting idle. And the kind of problems that can run, a lot. Any scientific computation that you can run with MPI that can scale out, has applications that do a lot of communication in between them, you can run that on my cluster. So if you have a cluster that's completely based on Ethernet, you won't be able to do that. And here brings us to the 20 gig InfiniBand. I actually have a picture to show you what it looks like. And finally, these nodes are dedicated. I've had these same 8 nodes for a long time, and access to my data, I have a little storage unit that's sitting somewhere else, which I have access to the data, used for accessing data that's using Ethernet. And for cloud, if you want to run computational intensive job on the cloud, you can only run embarrassingly parallel applications that does not require a whole lot of communication. So there is no magic here in terms of running computational intensive jobs. It's really the hardware, what kind of hardware you have. And several people have asked me questions prior to this session. One of the questions is that since these are virtual machines running on Windows Azure, how does it compare to a physical machine in terms of CPU power? So my answer is always, it's between 1 or 2%. You don't really see a whole lot. As soon as the Intel has virtualized these, Intel virtualization technology has made it to a point where you almost don't see CPU differences between virtualized instances versus the physical hardware. But all the machines that you're running, it's running on virtual machines. And it is pay as you go. However much money you got, you wouldn't have to pay for an initial investment, hundreds of thousands of dollars to buy the cluster, find a place for it to sit. It's definitely not sitting in my office. I actually had it sitting in my office. The first problem you run into with the cluster is that it requires a 20 amp outlet. I do actually have one, but if someone else is running something else on that, same amp, well, the circuit breaks, and the building manager comes up to my office and tells me that this unit has to move. And eventually, it did move to a data center. So for the Azure units, you're still looking at 1 gigabps Ethernet, and it's silent and invisible. And you can scale to as many nodes as you like for however much money you have. And finally, each of these units, for the extra large instance, when you have the entire physical machine, it's 8 cores. So that's quite a bit of computational power that you can have right there. And finally, if you keep your data on the blob storage, which is the storage unit that's sitting on Azure, then you wouldn't have to have all the problems that you would normally have by having to transfer your data from your machine all the way up to Azure. So my recommendation is always keep your data there if you can. So we're going to look at how the hybrid product actually works. So first of all, this is a traditional look of what a cluster looks like. You have a head node, which controls the entire cluster. It has a little database that sits on it that understands how many machines there are, and it keeps all the logs. And then the back end, you have the HPC cluster. And you can have up to 1,000 nodes. And for those really nice machines and hardware I've seen is that they have 24 cores now. They have 24 physical cores that you can run on each node. So you can have 24,000 cores at your command at a data center. And in 2000, 2010, we released a version called HPC 2008 R2, and that version is capable of running desk compute machines. So you can connect your Windows 7 machines to it. In fact, that's actually a very useful scenario. We had companies that wanted to buy hundreds and even thousands of licenses for these to add onto their Windows 7 machines and immediately make them into worker nodes on the HPC cluster. So you can do that. But of course, there are some limitations. Most workstations don't necessarily have the InfiniBand hardware. So for embarrassingly parallel applications where each unit of work is really well defined, you can do that. So for insurance companies and for those type of companies, or which you don't need to use MPI for very communication-intensive type of applications, then that is a perfect solution. So that brings me to the cloud. So it's actually very similar to Windows 7 or the client as a computational cluster. The reason is because the hardware is more or less similar because of the interconnects. So the interconnects on your workstations are typically Ethernet, and on Azure, they are typically also Ethernet. So if you don't have thousands of employees that can loan you their machines, so for a small company who need to just suddenly have 500 machines to run some computational intensive job, so Azure is the solution. So we have the next product, which is HPC 2008 R2 SP1. So SP1 fully supports Azure as integrated part of the product. And of course, I'm going to show you all the demos and how these jobs run. So, and the other thing I like to bring up to everyone here, how many of you are actually developers? There's quite a few. So quite a few developers. So as a developer, when you look at these different types of hardware and also IT professionals, you really want the user to be transparently using the client, the cluster, and the cloud. And I'm going to show you how that can be done from a user interface standpoint by showing you an application that I actually helped to develop. So let's look at Azure. So application in Azure is really simple, and you guys probably have seen the application as a service scenario where you are developing against a system where you have a web role and a worker role. So the way it works is that you make a request through the HTTP load balancer, and it gets sent to the web role, which is your user interface or your UI, and the worker role will take the computational intensive work and work on that. So I actually have a demo to show you. So here is an application that I helped to develop. In fact, it was the algorithm behind it is a traveling salesman or simulated annealing. Later, we changed it to a genetic algorithm for more people to be able to understand and also easier to parallelize. So the way it works is that you have, just like the diagram you previously saw, it has a worker role, and in the back end, I have a four-core worker role. And if I click on Monitor the CPU, you can see that I have a total of 4 cores currently idle. So this program or little demo, the way it works is that you can actually select a route which you like to do and click on Execute. And it's going to find the most optimal route for you to travel through all these different cities. As you can see, I use parallel technology behind this. That's why all the CPUs are lit up. And the way it works is that I use the task parallel library in .NET, which you can also use. And for the underlying computing, I am only using a very simple part of parallel task library, which is parallel for loop. So as I am computing the next generation of the optimal route using the genetic algorithm, I am simply sending those jobs and queuing it up through that. So as you can see, this kind of differs from a traditional web-based application because once you clicked on run, it's going to keep running for a little while. So what's going to happen to all the other users that want to access your website? So obviously, you need to be able to scale out to multiple machines. That's one way. And the second possibility is that you actually have a batch-based system where you have a queue that queue up the job that people want to actually run. And from a user interface standpoint, this is also poses a challenge to you. One is that, obviously, I can't have multiple people collaborate, not necessarily collaborate on a unit. So for this particular demo, I actually added a little feature called collaborative design. So what I did is I simply allowed the data to be visible to other instances of the Silverlight front end. And if I hit display, see how it runs. So you can see that this is the current run that I'm actually doing right now. So if I click on that and hit select display run, you can see that soon it will start showing the actual run that the other person is seeing. So these are the kind of considerations you have to bring into a web-based computational workload when you do this on Azure. So the interface plus the computation as a batch queue or possibly scaling out to add more instances as needed.
So this is showing the most efficient route of hitting each one of these island towns?
That is correct. I apologize for not explaining that earlier. For TSP, it means traveling salesman person. It's a NP complete problem, meaning that it's non-polynomial time. For me, it just means that it's extremely computational intensive. You can take, if you add more cities, it can run pretty much exponential amount of time that's going to require. So this is an example of a computational intensive workload. So, in the simplest terms is that your CPU is going to continue spinning for a long time by simply changing the amount of complexity you're doing. So for one city, it's very quick. For 50 cities, it's doable. For 100 cities, it's going to take maybe a day. For 1,000 cities, it may not complete until the end of the universe. So those are what that means is it's non-polynomial time. So let's let that run for a while, and we're going to go to the next topic here. So applications on-premise. I actually have a really cool demo today to show you how to design a car that is the most aerodynamic or efficient. So we're going to run that application on my cluster. So here's my Cray cluster on top, and underneath you have InfiniBand connectors. So the InfiniBand connectors are 20 gigabps. So you can see, those are the type of, those are, I think, copper connectors. Now you can actually have fiber, so they're extremely expensive. So the resources that you're going to need to run this application is that, first of all, you're going to need a dedicated nodes. So I have 8 nodes. I have 8 cores each, so that's 64 cores total. And each core can utilize up to 2 gigabytes of RAM. So that's 128 gigabytes of RAM. So that's still not quite doable on one single machine on your desktop. So the problem with this solution is that you have a cost of ownership. So first of all, you have to have $100,000 to be able to buy the machine, and there's a fixed number of resources that you can utilize. So I don't have another Cray. This is the only one that I have. So let's actually switch over to my machine here, and I'm going to run that for you. So for those of you who are not familiar with our clustering software, here's the cluster management console. So the cluster management console has the Wonder bar underneath here, and also the management tools in each of these panels. So the first thing you would do when you configure your cluster is to use the configuration. And so you have to actually go through a to-do list, and it's fairly quick. I would be able to deploy a cluster in less than an hour. Here our senior support engineer, Drew, is nodding his head, and he just did a deployment by simply clicking through the wizard and be able to deploy a cluster in an hour, was it?
Well, for this kind of stuff, an hour, where you've got lots of nodes and something like InfiniBand, if you're just setting up stuff on topology 5 for something embarrassingly parallel, 15 minutes.
Yeah, so for most of you who want to just try it out, it will take you no time at all. And in fact, I would encourage you to do that. And we have some Azure demos coming up as well through the same interface. So the way you would do this is to configure a network, and there are different topologies. And the simplest one is number 5, which you're doing everything on Ethernet. So that's probably, if you have a cluster of workstations you want to work with. So that's the perfect solution. And if you want to use something more advanced, like my setup is actually not in the list. The way it works is that I had public Ethernet on the public interface. And then on the private interface, I'm not using the Ethernet, I'm using the InfiniBand because it's the simplest setup for my needs. So each of nodes which are on the public network, you can have a lot more people accessing your cluster. So I actually have 8 people or more accessing my cluster, actually 16 people. So you can just terminal service in and use the nodes actually as a workstation if you really wanted to. So it's actually a very efficient and good setup. So it kind of gives you the best bang for the buck for people who want to do technical work and who want to share a very expensive piece of resource. So once you click through the wizard, it's going to ask you to provide installation credential. It's essentially your AD password and login, and then it will, you will name your nodes. It could be, cray 01 through 100, whatever you like to do, and also create a node template where you can essentially tell the node what it is. It could be a workstation node. It could be Azure Worker Node template. So essentially a template for the node you want to deploy. So later on, you want to create similar nodes. You can use these templates to be able to do so. And let's look at the node management. So here, you're seeing something called the heat map. I have 6 nodes up and running. I have several of them actually sitting. Actually, I have 8 nodes running right now. So you cray 01 and through 08. So these are on-premise nodes. These nodes are capable of doing MPI and other very communication-intensive jobs. And here we have Azure nodes. So these Azure nodes are added through a simple wizard. So you can simply say add node, and I can add that as an Azure node. And you can specify which template, which I just talked to you about, what type of template you want, and how many units you want to be added. So here I could say 10 or more, and specify the type of instance you want. So you have small, which is 1 core, 2 cores is medium, and 4 cores is large, and then finally extra large is 8 cores. So that is as large as we'll get for a single instance. So that's 1.6 gigahertz times 8 cores. That's a significant amount of computing power if you are able to spin at lots of these nodes. So let me start up the application and show you how the on-premise work applications that are using very chatty communication works. So here is a program called Cadium. So underneath, the computing engine is a very popular open source product called OpenFOAM. And what it does is it allows you to do computational fluid dynamics. So what we're actually solving here is a problem that is quite complicated. You have 600,000 cells in this simulation, so it's meshed up into the 600-cell representation. And then you're running a linear solve on this problem. And then what happens is that when you're done, you will be able to see what the flow or fluid flow looks like at the end of the simulation. So what you're actually seeing here is actually the end of the simulation. You can see how the air flows through the car when it hits the vehicle. So what we're going to do is we're actually going to rerun the job and show you how it actually works. So for any parallel jobs, the first thing you're going to do is to divide up your work. So you're going to write your mesh out, and you're going to divide the work into 56 cores that I have running for this particular job. So that's the first step. And the second step is that we're going to run an MPI job that will take advantage of the InfiniBand that we have with extreme amount of communication that's going through. So for now, you can see the decomposition is already happening. This is the first step. It's an MPI job. Even though it is actually an MPI job, it's really running a decomposition. It's taking your mesh and assigning them to each of the cores. And the way I am doing it is simply writing them to a file inside a directory for a particular core. So once the decomposition is done, as you can see, it's starting to do that. It's assigning the processor. It's actually doing the assigning of the processors right now. So I have a total of 56 cores on the cluster that are capable of doing MPI. And once the job has been assigned, it's going to start the actual run. So now it says it's still running the decomposition. And here we are doing very well. We're almost there. We're at 56 cores. And please keep in mind, these type of applications are extremely difficult to work with. So you have to edit your input files. You have to rewrite a lot of things. You have to do post-processing. To make the graphics happen, you have to go through easily 10, 20 steps. Here, I worked with someone to make an UI so that it's a complete full integration with the HPC server. So let's take a look at the actual node. So I already finished, and you can see that even though it does a lot of communication, it's still able to peg the CPU at almost 100%. So as you remember that the number one rule is that we want to utilize as much of the CPU in terms of percentage as possible. So the CPU utilization is goal number one for HPC applications. So as you can see, it's chugging along, and it's doing fairly well. And the other thing you can actually take a look at is the disk activities. So for most traditional HPC apps, you don't tend to have a lot of I/O that's happening. And what's interesting here is the Azure nodes are actually much more chatty than doing more disk I/O right now than the actual Cray ones. So this is my first demo for computational intensive jobs that requires traditional HPC hardware. So the second run I want to show you is a weather simulation. So for this particular conference, I actually ran a weather forecast for Atlanta. I ran that when I got on the plane on Monday, and I wanted to run that for 8 days. So here's the actual output that I want to show you. So I'm going to show you the visualization and output first, and then we're going to look at how the code actually works. And the nice thing about this is that you would be able to do that yourself if you follow me on my blog. I would actually show you how to be able to do that on your home computers. So this is very interesting to whoever are technology enthusiasts who want to see their computer in action, and also serves as a benchmark for a lot of people who want to know how fast their hardware can run. Okay, so here is two movies which I want to run. Let's see, let's open it up again. Allow content. So this is a forecast for Atlanta from the 16th through the 24th. So this is the humidity, I believe. So if you can see that this is the actual visualization of the computing that you actually did. And here's another one. I think that's the actual cloud that you're seeing. So for weather research and forecast to run, you also do need very efficient interconnects. So there you go. So that's what I actually ran. If you actually take a look at the top, these are the things that I actually wrote down for what you would have to do let me see if I can make this a little bigger. Oh, no, I can't. So it's very complicated. There's a lot of steps that's involved. So first of all, you have to get your data. somewhere from NOAA or NCAR that's current. So that's the boundary condition for your run. And then you have to actually put them through all these post-processing tools and make them look pretty. So the actual movie that you saw, that takes a significant amount of work to be able to just produce that. So that brings us back to the question, can we actually move these type of applications onto Azure? And we'll have a discussion on that in the next few minutes here. So let's actually take a look at this little car here. So the car is almost done. So what you're seeing there on the right corner, that's residual, meaning the error function is whether your simulation is converging to a solution or not. On the lower right, you're looking at the lift and drag as you are traveling through the air for your vehicle. So who can actually tell me how fast this car is currently running at? So it's actually right there on the graphics. How fast is the car currently running? Anybody? Well, if you actually take a look at the color bar, it's running at, the vehicle is mostly green, and it's running at about 37 kilometers. As you can see that when the air actually hits the wheel, the speed gets reduced. You can see that is running at 1 or 2 meters per second, or kilometers per second. On the wheels, that's actually in a different color. So the actual entire vehicle is running at the speed of the air that's flowing through. So that's my demo, and for on-premise applications. So let's actually take a look at some hybrid models. So we just saw also saw the weather forecast. So the way it works is that you simply enter a longitude and a latitude and enter a script. And you saw the description which I put down. The description pretty much tells you what you're actually doing. And you run through that process of getting the data, running the data, and finally produce an output. So this is how a lot of these applications work. You have a workflow that comes with the actual computation. So the next step, which is the most important part of this presentation, is Azure and HPC integration. We're going to go through several examples. The first concept I'd like to explain here is embarrassingly parallel applications. Those are the kind of apps that each unit of work is really well defined. So we're going to do 3 demos. One is that we're going to make a movie. So we're going to render frames of a movie, and then we'll combine the frames and make that into a movie. And the second demo I'm going to show you is running an Excel spreadsheet and be able to spin out 300 cores all at once. Be able to peg 300 cores on both on-premise and also Azure cores at the same time. So those are the 2 demos that I'm going to show you. So let me go ahead and cancel this CFD simulation and prepare the cluster to run the actual, the next demo. So first of all, let me explain to you how the Azure Burst scenario works. So on-premise, we already explained that. So you have a head node, and you can control either workstation nodes or cluster nodes. So the cluster nodes are server nodes. And then, for us to connect to the internet, you are actually using connect to the Azure nodes. You're making that connection through internet. That connection can vary depending on what internet service you have. So for me at home, I'm running at Comcast, so that's actually fast enough for me to do a lot of things already. So for people who are on an enterprise network, you have probably a lot higher bandwidth. So for those of you who are traveling, who has a netbook and want to be able to control Azure nodes, it's actually quite doable. In fact, I actually had a netbook which I installed Server 2000 AR2 and was able to control all the Azure nodes which you saw running on my cluster. So bursting into cloud, the type of applications you can run is mostly applications that don't talk to each other so much, for the various instances that you're running. So embarrassingly parallel, mostly. So each unit of work is well-defined. So if you're making a ray tracing job, you want to farm that out to multiple frames. That's embarrassingly parallel because the first frame doesn't really care about what the second frame is doing. And if you're doing a Monte Carlo simulation for pricing your options, so that is also very much embarrassingly parallel because you're calling the web service as an independent unit of work. So let's look at some examples here. So here is an application which I mentioned. First of all, this application uses two parts. One is that the computational engine is using our SOA support on the Windows HPC product. So essentially what you're doing is you're running a web service 1,000 times. So the same web service is loaded on multiple nodes at the same time. The second interesting part about this is that it uses VSTO, which is Visual Studio Tools for Office. It lets you programmatically write a spreadsheet. So you can say, I want to create a spreadsheet which has a workbook, and I want to create sheet number 1 and number 2. Inside that workbook, you can actually write C# code to call the actual compute service. So let me actually do the demo for you here. So this program is just simply a Visual Studio project. And as you can see on the right-hand side, you have a service that's defined and a service reference that's defined. It's called Asian Options. It's really simple. You have just the pricing of it's just one function call or a web service call. And on top, you have a workbook, which has sheets number 1 through 3. And let's actually, the most important part of this is that you're actually going through each of the sheet and computing the Monte Carlo runs of your Black-Scholes model. So it's a Monte Carlo simulation. It's randomly trying to do the random walk and figure out the best pricing of your option. So let's run that. So if I hit run, it actually starts a spreadsheet. So what I'm going to do is going to hit submit. And as you can see, that it submitted job 10,462. And let's actually look at what the cluster is doing. So it started the service. And the most interesting part of this is actually the heat map. As you can see, that the on-premise nodes are already starting to think about this problem. It's starting to get the service ready and starting to do the computation. And soon they will all reach 100% in terms of CPU utilization. So I have almost all the nodes already started up. They're running at 100%. And the nodes that are sitting on Azure, that's in the Chicago data center. So this machine is sitting in Seattle. So somehow I have to tell those guys, hey, wake up, time to run some simulations. So that's going to take quite a while. So much longer than if you were simply walking over to the data center and say, hey, you guys start running. So as you can see, it starts up, but there is a delay in that. So sending the job over, having the queue to prepare the jobs to run, and have them actually starting the run, it will take some time. So now, as I stated previously, they're embarrassingly parallel, meaning that all the CPUs are pegged to 100%. So there's no communication involved. The CPUs are free to work on their unit as much as they can. So as you can see, that the on-premise nodes just finished their work. So they first got the work, and first they finished the work. And it's going to take a few, I think 20 seconds or so, for the actual work to be finished by the Azure nodes. So in terms of the computing power that is contributing to this spreadsheet, the actual Azure cores contributes to half or more the actual computing power, because when you have 8 cores times 15 units, and that's 120 cores that you're actually working on the problem. So I have a question in the audience.
Does the scheduling for the local nodes
Yes, it also depends on... What did I do? Okay. Oh, that's right. That's the speaker. That's right. So, yes, it depends on how you schedule it. It does prefer the local nodes. Yes, I'm sorry. So the question is, does the scheduler prefer local nodes versus Azure nodes? Yes, it will schedule them first on the local nodes. And if, in this case, I said I want to take all the nodes you have, instead of just simply saying, okay, I want the best nodes that I have, I would say, I'll use anything that is available. So for the nodes that you want, you can specify a group for them. So you can specify a group. So here, on the right-hand side, as you can see, I actually specified a lot of these nodes myself. So there's the Wharf demo nodes. So there's 1, 2, 3, 4. These are the nodes that I want to run Wharf. And then there's the broker, which is actually taking the communication and spreading it out. There's your broker node. And then there's, I think my friend Brian, who was using my cluster the other day, and he has created his own group. So it really depends on what you want to do, and you can fully customize just about everything. And if you want, you can submit your job to only run on Azure nodes. So does that answer your question? Okay, you have, okay.
I assume you did not segregate the nodes. You said you submitted to everything.
That's right.
There are 2 idle nodes. Every time the scheduler chooses the local node versus the Azure.
That's correct. So if you have nodes that are idle sitting local, it will always choose the local nodes. And then when it needs to, it will use the nodes that are further out.
And that's not because the Azure nodes might be a slower CPU. It's because they're Azure nodes.
That's correct. Yeah, so that's just how the scheduler is designed to do. So let me actually go back to my slides and explain was another interesting problem. Movie rendering. So the next demo which I want to show you is to take lots and lots of movie frames and start working on them only on the Azure nodes. So the problem with this particular case is that the movies that I'm rendering has input files. So the description of the 3D model is rather big. So each of these are 20 megs or more. Just step away from the speaker. So for me to render all of that, so I would either choose to render all of them on-premise, or I would render all of them on Azure. So for me to run this on Azure, I have to ship about 8 gigabytes of data all the way out to Azure. So there are several things you can actually do to reduce that. One is that the first thing I do is I want to see if the data is compressible. So I want to compress the data. And the second thing I do is see if I can create multiple connections. So that way I can make sure that these connections are able to send as much data as possible, given the limitation of my pipeline. So in this particular case, I had 8 gig worth of data, and I compressed it all the way down to maybe 1.5 gigs. And 1.5 gigs is really not that much data. So actually, he's transferred that through my Comcast connection. That took a couple of hours or so. And then I just kept all my data on Azure data storage for the whole time. So from now on, when I do this demo, I don't have to worry about the step, which takes 40 minutes, would be the end of the session now, right? So you don't want that. So let me actually show you the demo. So the first thing I would like to show you is the tools that I used in this particular demo. So the first thing I like to do is I always show people how big these frames actually are. So if you take a look at these frames, these are the 3D data sets. If you uncompress them, they're much, much larger than what it looks like. And so that's my input directory. I'm using a product called Cloudberry, and you can use whatever you want to browse through your data storage. So here's my input. And what I want to do is I want to have Azure render my movie and send each frame back into the storage, which is the output. So here's my output directory. So I did a run this morning, as you can see, much earlier, and they all finished. So let's actually start running that. Okay, so the way you submit a job is actually quite easy. You go to Job Management, and new job, and I want to pick a predefined XML file, which I did. So this particular job is simply doing a simple command 400 times. So this is our parametric sweep engine. So what you're doing here is you're running the run command and run that 400 times. And for each of these movie frames, it's the same command for each of these. And let me go ahead and submit that. So you're probably curious about what is the actual command that I ran, right? So let's take a look at that command. It's really quite simple. There you go. So let me see if I can find that. So here's my run command. I've simplified it to make sure that everybody can understand this. So the first step I did is to do Azure Blob copy. So the storage is sitting somewhere away from the compute nodes. It's your permanent storage. And then the compute nodes can be spun up as you want. So for me to do a frame or a compute, either I have to have a file share, which Azure doesn't have a file share. I would have to copy the data file from the blob storage to the unit that is being computed, the compute unit. So what I did is I copied it, used Azure Blob Copy, which you can actually download off the web or go to my blog, and there's a sample for that. The second thing I do is to take that zip file and unzip it. Once you unzip it, it becomes tremendously larger. And then the next step is you do the actual rendering. So after you finish doing the rendering, you have to copy your data back to the blob storage. The reason being that it's persistent. So if you keep it on your node, when you turn it off, it's gone. And there's no way that anybody could help you to get it back. So it's just one of those units that you got from the Azure data center. So copying it back, you will have the actual nodes. So let's actually see what's going on with my cluster now. It's actually really computing now. So let's look at all the Azure nodes. They should be, as you can see, they are, since there's a little bit of data involved in terms of movement, so you have to copy your files. So they're not being utilized at 100%, even though this is an embarrassingly parallel problem. So all these units are now working on the frame. So each of them pick a frame and work on it, put it back to the blob storage. And think about it this way. I have a laptop that has only 2 cores. And for me to render the entire movie, which has 400 frames, it's going to take about 15 to 25 hours. So I don't have that kind of computing power with me. But if I actually do have SP2 installed on my machine as a separate partition, I can simply go on that partition and burst down to cloud. If you have a VM, you can install it inside a VM. Burst to the cloud and keep my data on Azure and simply do the computation right there on Azure. And so since this is 12 cents a core per hour, so I am using about 120 hours. So it's, I don't know, it's $1.50 an hour. So if this finishes in about 5 minutes or 10 minutes, it's only going to cost me $10, $15. So this is quite doable, given the type of problem is suitable. I have a question in the audience. Go ahead.
Does the rendering actually require special software on the Azure?
Yes. So you have to copy the actual software onto the Azure nodes. And let me show you how that's done. So in my blob storage, there is actually a software being installed. Hold on, give me 1 second. So in my blob storage, I have a HPC pack directory. So this is all the software that you install. And the way it works is that you simply zip it up. You zip up your executable with all the things that it needs to contain. And we provide you with a utility. So the first step to install this is you say HPC pack create. You create a zip file. It will create a zip file for you. And then you say HPC pack upload. And you will upload that to your blob storage. And you need to provide it with a key, obviously, a storage key. And the third step, you say HPC sync. And then every single node that you spun up will have that. And if you add more nodes, it will automatically synchronize that upon the next creation of new nodes. So it's a simple 3-step procedure that you have to do. So you say HPC pack, you create your package, which contains your binary executable. And the second step, you upload the binary storage executable onto the blob storage where you keep all your applications. And the third thing is you run HPC sync to update every single node with all these applications. So there's simply an executable. So there's no registry that you have to deal with. It's just simply 3 commands that then you have all the different nodes. Let's actually take a look at the progress of the actual work. So let's see. So they're still working on it. Let's look at the job progress. It's 94% done. And you would probably ask me show me where's the movie and where's the files. So we can just simply look at the blob storage and see, do a little refresh and see if they're actually working. So this is Redmond time. And as you can see, it's working fairly well. And it almost finished. And it's simply doing the rendering, copying the TIFF image back into the storage. Okay, so that is the second scenario where you actually have data involved. So I provided you with a little utility which you can copy files back and forth. And for installation, it's a 3-step, easy 3-command procedure that you can HPC pack and HPC pack upload, and then also sync. Then every one of your nodes has this job, and you can simply run it as a command line, and which are very simple. It's just a DOS command, which you kind of sandwich the data operation with a CPU operation. So the CPU operation being the actual rendering command, and the data copy to emulate a file share. So let's go back to my slides here. So here's another example. So there is a company that I'm working with, which is called Optimal Solutions. So they make these optimizers for various engineering products. They're very famous in the NASCAR or Formula One car race. So essentially the idea is that you want to run your design optimization through multiple parameters, but produce the same thing. But here you're running very short jobs. You're giving it slightly different modified geometry of a particular product. And then once you take that, it would be able to submit 500 jobs onto the cluster or Azure and run the design optimization and find the best design. So this is kind of the future of computational fluid dynamics and other type of computing work. So the way it works is that it uses something called Latin hypercube. It's just a statistics method. So given amount of, it will guarantee that your sampling will be the best, given however many sampling you want for a set of data. So for example, if I'm saying I want 1,000 different variations of the geometry from the circumference to the size of the intake, so I simply select a few variables that I want to optimize, or the speed of the flow, and simply click a button, and using a statistics or math, you would be able to produce the sampling that would allow you to know your cost up front. I want 1,000 runs, and it will pick the best ones for you. And once you do that, we actually had a run that was able to do a lot better. A couple of days' work is better than 60 humans working on it for months. So design optimization is embarrassingly parallel, but yet extremely powerful. And the nice thing about this is that your use cases, your actual CFD runs, are small, but at the same time, these runs are generated. They're auto-generated. They're not generated by a human. You're just simply using statistics to generate your cases to utilize the amount of cores that you can have on Azure. So this is actually a real case study from the Ford Motor Company. And finally, I have another demo, which I want to show you, is to use Silverlight to visualize a simulation that you finished running. So this is the LA earthquake simulation. that the data actually ran on a cluster. So the simulation ran on a cluster, and we found this is to be an excellent way of showing the work you have done to use Azure. So the front end is a Silverlight, and the back end is either a SQL Server, SQL Azure, or you can keep them in the blob storage once your job finished running. So it's really difficult to move your data back and forth between your nodes, your on-premise nodes and on Azure nodes. Reason simply because of the limitation of your internet connection. But at the same time, you will be able to do all of these by adding visualization components so that the data doesn't have to be moved back and forth when you actually do the visualization. So this is a recommendation that I make, which is to keep your data on Azure if you want to work on Azure and do everything there. So by adding these components, you can share your data much better and also be able to not having to move your data. Let me go back to my PowerPoint. So here's the summary. I have 9 tips for best practices when you are working Azure and HPC. So the first thing is that always consider the total cost of ownership. So if you can use Azure and you don't have a data center, Azure is a perfect solution for you. And your barrier for entry is simply one node. You just have to install it on a head node, and now you suddenly have the power of Azure. And use .NET Parallel Library to take advantage of multi-cores, so we can have up to 8 cores. As the CPUs become having even more cores, it becomes critical for ease of programming. So for those of you who want to simply use only Azure, or if you want to scale out in one node, either on desktop, cluster, or on Azure, the best way to do this is to use .NET Parallel Library. So for the simulation you saw, it was simply doing a parallel for loop. It's taking 1,000 workload and queuing it up for the amount of CPUs that you have. And for Azure Burst scenario, if you want to use, if you want to scale out to multi-cores, multiple nodes, most of these work would have to be embarrassingly parallel. So that's the best type of workload that's suited for Azure. So there's not much communication that's involved. Our parametric sweep engine, which you saw, which is simply running a batch job through iterations of multiple parameters, that is very powerful. And you wouldn't have to write any program to simply use that by not having to write much programming. So you're simply writing a script that includes a copy step and also the compute step. So when you have multiple users, so you have to have, for HPC applications as a service, you have to have multiple user considerations. As you can see, once the guy clicks on your web page, that's going to be working for a while. So the next person may not be able to do work immediately. So that's why you need a queuing system, or you will have to create new nodes as you do that. So for HPC SP2, you will be able to do that. So we have a REST interface which will allow you to do that, which I did not cover here, but the idea is that whenever you need to do computational intensive jobs as a service, you need some kind of management and scheduling mechanism, and HPC is a very good HPC job scheduler is a very good solution for what you want to do. And also by providing your user with a transparent experience. So the transparent experience is that your UI should not have to be very different from the cluster, the client, and the cloud. As you saw on the example which I showed you, you can simply change a parameter by selecting a different type of compute resource from your application to be able to do that. And also, you have to obviously minimize the amount of data transfer you want to do between your on-premise nodes as well with the what's actually on Azure. That's limited by your internet connection. So either keep your large data sets on Azure or keep your large data sets on-premise. So, and if you have smaller problems, which you can move a little bit of data by pre-staging them, that would be fine. It's just that you do want to minimize that and maximize the amount of CPU you can spend on your computational intensive jobs. So this is the example which I showed you. And on the pull-down menu, I can actually choose cluster or the cloud, depending on what you have. For the cloud computation, you have to enter a username and a password to be able to access the cloud compute engine for this CFD simulation. But for that particular problem, it would actually have to be fairly small to fit on the cloud. So I actually have a quick demo later on after the session, which for those of you who have time to stick around. It simply does an HTTP request by zipping up your data set, sends it to Azure, and when the job is done, it pulls it back down to your local node and displays it. And here are developer benefits. One of the things that we asked, questions we had in the audience was, how do you package up your application? So the application is really easy to be packaged because you don't have to recompile your code just for Azure. You can simply take your Windows binary and run it on Azure, and it's the same binary that you have to work with. And better tools, we have Visual Studio and other tools that you can work with to make your experience, a developer experience, a lot better. And here is a ecosystem which I have been supporting for the last 3 years. And a lot of them has to do with HPC computational intensive jobs. And the way it works is that we work with compiler vendors, we work with build systems, we work with solvers and data I/O libraries. And then once you have those done, you can have chemistry code, you can have structure analysis, climate code. So all these kind of depends on having number one and number two, which are the libraries and the tools that you need. And also, visualization is very important to us. And I actually have a little movie that I want to play, which shows the hurricane running. A hurricane simulation we ran a while back. And here it is. So here's the movie that I want to run. And I think I ran that last year. So this is a visualization tool that I worked with Livermore to, so it's very capable. It's capable of taking NetCDF or the weather simulation data and pull that in and visualize a 3D simulation. So you don't have to just simply look at a 3D environment. And you can overlay a lot of these information on top of each other and make a movie out of it. And now it's going to show the wind speed as a vector diagram. So for us to make sure that HPC is really going to work well for everyone, we also work on the ecosystem and make sure that everyone has the tools they need to be able to not simply run their job, but also look at the data sets. So we actually have very large customers all over the world that actually uses Visit right now to visualize data on a large cluster. And here is the roadmap for us. Currently, we're at SP1, and that was released in, I think it was December of, yeah, that's right, December of last year. And the next release is going to be June 2011, and currently there is a beta on connect.microsoft.com. So it's capable of running MPI. Like I said, for MPI jobs, we don't have the hardware that's required to run really large simulations for problems that have very chatty interfaces. But you can run that in one node. And oftentimes, as you can see from the design optimization example, you can do a lot of damage with just 8 cores that you want to run. And a lot of these software, you can scale them out as you as much as 8 nodes if you really wanted to. Some of these software would run up as much as 64 cores, and some of them may be a bit more. But of course, not having the right hardware, it's going to suffer a little bit when you run them on Azure. So we also support VM role, so you can actually package up your own VMs and upload that as a compute instance. And also we support over and under subscription of the nodes. What that means is that if I had an MPI node running, it's not using all of the CPUs. It could be using 50% of the CPUs because of communication overhead. I could be running an embarrassingly parallel application on the same node. I could be running Asian options on top of it. So that means I can submit multiple jobs to one core or one node with the same resource to be able to maximize my utilization. And finally, we are going to provide you with a web portal for job submission, which Drew actually showed in his session yesterday. So you can use a web portal to submit your jobs instead of using the management console. And also now we have smart card authentication for those of you who really need very high security to be able to use very expensive hardware for specific users. And I like to actually have you take a look at my blog, which has a lot of information, from simple examples to very complex simulations, and also status of many popular HPC codes. So for this particular blog, which I described the sample that I put up, so there's a white paper and also 5 very small samples. So I think if you spend less than an hour, you would be able to have and with a subscription, Azure subscription, you just need one node to be able to use as many cores you can afford on Azure. So there are examples that help you to do these type of embarrassingly parallel programs. And also the image rendering example is also on the same web page. So if you go on my blog, you would be able to see a lot of these information in real time as they become available. And I will also make the weather simulation as well as the CFD simulation available in the very near future for those of you who want to do that type of technical computing applications. And finally, if you read the paper, it would give you even more information about how to do data analysis, including the benchmarking of communication between the nodes to the blob storage, and so you can optimize for and simulate for the type of technical computing workload that you want to actually do. And if you download the SP2 beta from connect.com, I think it's good for 60 days or 180 days. I think it's good for 180 days. And that would be more than enough time for you to be able to use until the next version comes out, which is in June, which is our final version. And also try and download the Azure Burst sample and to see how well it works for you. And here are some of the related contents. Tomorrow we have another session by David Chappell, which explains a lot of these models to you, including Dryad Link or Link to HPC product. And also here are the resources that I would encourage you to take a look. And thank you very much for staying here. Any questions? Yeah.
Have you ever
Go ahead.
experimented with a scenario where data is being uploaded as the job has already started? So it's a large data set with a lot of units of work where it might take a long time to upload, so maybe the jobs can start running before all the data has arrived?
Yes, you could do that. So the question is that would you be able to start computing before all the data has arrived? You would be able to do that, but you have to be very specific about where which units has arrived first. So you have to kind of script it for a specific worker node to be able to do that. Otherwise, if you do it through the parametric sweep engine, it's not going to know which resource is available versus which compute node is available. So it's going to require a little bit of work to be able to take advantage of that. But in the most part, you would have to move all your data up. Otherwise, you have to do a little bit more intelligent work or in terms of scripting. So any other questions? Go ahead.
Best practices for
Right. So the question is, what is the best practice for debugging your software in terms of being on enterprise versus being on Azure? So I would do the following. First of all, I would just test everything thoroughly on premise first. Actually, one unit first, right? So you test it on one machine, your workstation first, if you're a developer. And the second thing is you try it on the cluster, see if it works well on the cluster, and take notes of performance data. And the third thing is I would copy it onto Azure to make sure it works well on Azure. So a lot of the times, if you have applications that don't even work well on cluster, it's not going to work well on Azure either. So it's about taking your application, work it through the easiest testing method as possible, and then you move it onto Azure. And in most cases, it pretty much runs as well as you would do normally on premise if you don't have a lot of data involved. So the other question is that what happens if you have a runtime error on Azure? Well, there's a couple of things you can do. On SP2, you're actually allowed to terminal service in and look at what exactly happened on that node. So that's one of my favorite ways of debugging. And the second way is that you obviously can turn on a lot more logging. So logging is also very important, but I don't think you can debug on. You can't hook up your debugger on Azure. But if you install your debugger WinDBG on Azure node as you're logging in, that's definitely doable. Any other questions? Okay, thanks.